All right, guys, so let's take a look. This will be lesson 12.1. We're getting into slope-intercept form. So still dealing with linear functions and slopes and y-intercepts and all that stuff. So let's see if we can take a look at a situation here and kind of keep working on this slope and y-intercept. So if we take a look, let's say Owen's water bottle leaked in his book bag. He did the following experiment to find how quickly the water drains from a small hole. So let's pretend like we had a water bottle. We poked a small hole in the bottom of it, and we made sure the hole was on the bottom. And we're going to draw a line on the bottle every 5 seconds to mark the water bottle. Okay, so just to kind of visualize what's going on, let's say, I'm not a great artist here, but let's say there's a good old water bottle. And let's say, at the beginning it's full up to here or something. And then 5 seconds go by, right? We're poking a little hole down here, so all the water's going to drip out. 5 seconds go by. Let's say that the water level is now down to there. And another 5 seconds, another 5 seconds, and so on. So the water's clearly going to get lower. And I'm not actually going to do this. I don't want to make a big mess and everything. But let's just pretend like we did. And let's make a table of values. Let's just, again, kind of pretend. Let's say let's just say for the initial height, let's say it was like 15 centimeters. So at time 0, before we even poked a hole in it, let's say it was 15 centimeters. And then 5 seconds go by. Okay, so I poked a really tiny hole, so it's leaking slowly. Let's say it went down to like 13.5. Let's say at 10 seconds it went down to 12 centimeters, then 10.5, then let's say 9 centimeters, 7.5, 6, 4.5, and 3. I'm just making up some numbers just so they'll fit on the grid that they gave us here. Let's go ahead and plot the points. Let's see what's happening. So as time goes on, okay, here's our time in seconds. We want to see how is the height of the water changing. Okay, so the first ordered pair I would graph, when time is 0, the height is 15. So 0, 15 would be there. Okay, and then as time goes by, 5 seconds. Okay, so this would be 5 seconds. We are at 13.5. Okay, so somewhere about there. 10 seconds go by. The height is now 12. Let's just do a couple more. 15 seconds. So 15 would be right in there. It would be at 10.5. And let's just do one more here. At 20 seconds, let's say the height is 9. So right between the 8 and the 10. Okay, and that would appear to look kind of linear, right? Kind of got this little constant steepness, constant slope going on. And it's a negative slope this time. Okay, I can tell because as we move to the right, the y values are getting smaller. Okay, just like when you read words, when you read a sentence, you read from left to right. In this case, as I read that graph from the left to the right, the y values are getting smaller. Again, that indicates a negative slope. So does the relationship between time and the height of the water appear to be linear? Okay, does that look linear to you? Yeah, I think it does. I mean, there may be some slight variation. It might not be the exact same rate of change, but yeah, the graph appears linear. Okay, because we would probably expect the amount of water that's leaking out to remain fairly constant. So let's say, yeah, definitely looks close, right? Somewhat linear. All right. Of course, we had specific points. We plotted just single points here and here. But for example, we could have measured the height at 9 seconds. If I wanted to get an idea for 9 seconds, I could kind of measure this up here and say, there was about, I don't know, roughly 13 or so. Trying to line that up. Okay, I don't have to jump from one point to the next. I can kind of get the slope of the line. Just like before, slope will always measure the change in the y values. Okay, so let's just go from, let's use these 2 points. Okay, the change in y value to the change in the x value. Okay, and if we look at our table that we used, okay, I used the points, let me just rewrite them here. We used these 2 right here, which was 15, 10.5, And then the next one I used was at 20 seconds, there was 9 centimeters. Okay, so the slope here, the rate of change, if we take a look at the change in the y values to get from 10.5 to 9, okay, the change in y values was down. Oops. The change in y values, let me get a marker here. Change in y over change in x. The change in y value, again, from 10.5 down to 9 was down 1.5. While the change in x values to get from 15 to 20 was positive 5. Okay, so negative 1.5 over 5. And again, on the graph, here's the negative 1.5 down and then over 3. I'm sorry, over 5. Okay, so that would be the slope. Now, usually you don't want to have a decimal within a fraction. So if it's negative 1.5 over 5, it would probably be more common to times top and bottom by 2 and make them both whole numbers, just so you don't have fractions or decimals in the mix. So we could say negative 3 over 10 would be our slope. Okay, y-intercept always refers back to where did we start. Okay, so if we look, this thing started up there. Okay, when the x-coordinate was 0, the y-coordinate is 15. Let's keep going. Okay, so discrete data, okay, are data that can only have certain values, okay, such as the number of people in your class. So on a graph of discrete data, there will be space between every 2 possible values. Now continuous data, so there's 2 types of data. Continuous can take on any value within a range, for example, height. So like if you think about your height, right, as you grow, you kind of go through all of the values. You're not like one day you're not 5'1" and then the next day you're 5'2". Like you gradually kind of went through every value. That's continuous growth. So discrete, okay, again, discrete would look like just a set number of points. Okay, like this could be the number of students in attendance on Monday, Tuesday, Wednesday, Thursday, and Friday, for example. Okay, and we'd plot how many people there are. Okay, there's just a fixed number each day. There's nothing in between. Continuous is more like the graph we did. Okay, now smooth graph with all of the points in between, right? Okay, so the one we did was continuous. Okay, again, even though we just plotted specific points, once we draw the line through it, that's going to kind of allow it to be continuous. I think I missed a U in there. C-O-U-S. Okay. But anyways, more on that later if we need that. So anyways, the slope of the line, okay, so the points that we graphed, 3/10, negative 3 over 10. All right, and what about our y-intercept, part B? That's the y-intercept. Okay, the y-intercept is 15. Okay, or we could write it as an ordered pair. X was 0, y was 15. All right, can we describe the meaning of the slope? Okay, sure, we got a number. Now, what does it mean? So if we go back to our situation again, let me just draw it here. Remember, we were doing time, and then we were doing the height of the water, right? So if slope is change in y over change in x, okay, that means that these numbers are telling us that the height is going down or decreases 3 centimeters every 10 seconds. Okay, the height per time. That's what our y over x was. Okay, and then the y-intercept, what does it mean? What was the 15? So the 15, again, occurred when the time was 0. Remember, we started off up here at the point 0, 15. So what is that telling you about the situation? That was going to be the starting height, you know, before you even poked a hole in the bottle. Okay, and that's what a y-intercept generally is. It's an initial value or a starting value. All right, so let's see if we can get an equation here. Okay, and if we think again about our situation, the equation, or the data was actually the height, and time was actually the x value. Let me just draw the first couple rows of the table so we can see it. It was time and height, just so we can see it again. When time was 0, we were at 15, and we went to 5 seconds. The height was what, 13.5? Okay, so, and then it just continued on that pattern of down, down, right? So the equation, again, if we want to think about this line that we drew, it started at 15 and kind of went downward that way. The height, okay, the height was always starting at 15, and then we were decreasing. The slope we had was 3/10. Okay, so it was going down 3/10 for every second. Okay, so the question is, how does the coefficient, so coefficient, what that means, the coefficient is a number that gets multiplied by a variable. Okay, so in this case, the coefficient is this number here. How does that coefficient relate to the experiment? Okay, the coefficient on the time variable is the slope, isn't it? It's the rate of change. It's the -3 centimeters per 10 seconds rate of change. Okay, so anytime you write a linear equation like we did here, the coefficient on the x variable will always be the slope. And notice what else happens in number 8. The constant term, okay, so constant term, what that means, constant is just a number without a variable. Okay, so the 15 in this case, it wasn't getting multiplied by a variable, it was just 15. That is going to be the initial value, okay, also known as the Y-intercept. Okay, and that's how linear equations are always going to work. You're going to have a constant Y-intercept plus or minus, depending on if the slope is positive or negative, the slope times the other variable. Okay, so let's check our understanding. Let's practice another setup of a problem here to make sure we're clear on the concept. So number 9 here, can we find the slope of the line that passes through those points? Let's take a look. So slope again is always the change in the y value over the change in the x value. Okay, so what we're going to do is check the change in the y value. So to get from 11 to 7.5, that was going down by 3.5. Okay, so again, to get from there to there was minus 3.5. And what you can do to get that number out, you can do 7.5 minus 11. Okay, just do the second number minus the first number. While the change in x, to get from 0 to 2, it was up 2. Okay, again, that would be 2 minus 0. And here's another case where we don't really want to leave a decimal mixed in there with inside of a fraction. So what I would suggest on a problem like that is just times top and bottom by 2. As long as you do the top and bottom, it'll keep things even. So -7/4 would be our slope. Okay, and notice one other thing too. If we would have just used the first point and the third point, we could have come up with our answer without getting a decimal. Because notice, to get from -11 to 4 is down 7 here. And to get from 0 to 4 and the x is up 4. So you could have just used different points in the table, but they're all going to be equivalent values. They might just need to be reduced. All right, and lastly, to check your understanding, so Ben's Bells, a community service organization, began hanging ceramic wind chimes randomly in trees, on bike paths, and in parks in 2003. So a written message on each bell asks the finder to simply take one home and pass on the kindness. Okay, so 1,000 bells were hung in 2003. The number of bells increased by 2,000 each year after 2003. So let's complete a table here. Okay, and notice, here's a key, sometimes problems do this, the x value will be the number of years since the initial time. So we're going to assume 2003 is like our starting time. Okay, so that's going to be, it's going to have a 0 here because that's 0 years after it started. It's like the initial value. Okay, and they told us straight up in the wording, in that year there were 1,000 bells. Okay, then we know the number of bells increased by 2,000 each year. Okay, so in year 1, there would be 2,000 more bells, so 3,000. Okay, in year 2, there would be 2,000 additional bells, so 5,000. And year 3, even 2,000 more bells. Okay, so 7,000. Can we make a little graph here and talk about the situation? Let's take a look. Okay, so we have 0, plot the first point, 0, 1,000, okay, would be right here. Okay, then at year 1, the Y value is 3,000, okay, the number of bells. Year 2, the number of bells was 5,000. And year 3, the number of bells is 7,000. Okay, so we plotted our points there. Now let's think about, is this one an example of a continuous function or a discrete? Now this one, is it possible to have a like a fractional number of bells? Okay, it's really not, right? There's only going to be a whole number for the number of bells. So in this case, this is an example of discrete because it does not go through all possible values. It's not like the previous example where we were measuring the height of the water. Okay, the height of the water goes through all values, fractions, decimals, all that stuff. Okay, this one cannot. So this one's actually discrete. Okay, so can we use the data in the table or the graph to write an equation? Okay, let's think about the situation here. The situation for the number of bells, they want us to call that n, given the years since 2003 t. So they want an equation to get the number of bells. So we're going to do something like n equals, and let's think about the situation. Okay, what are we starting with? And then what's the rate of change? Okay, we are starting with 1,000. Okay, and then each year they are adding 2,000. Okay, so we start with the 1,000, then we could say plus 2,000 times t. Okay, t again is the years since 2003. Okay, so using the graph, in 11, determine the slope and y-intercept. So let's take a look. So the graph that we have there, the slope is the rate of change. Okay, so the slope is the rate of change. How much is it changing each year? 2,000. Okay, there's 2,000 more bells each year. And the y-intercept is the starting value. Okay, and again, we're considering 2003 as the beginning, so we started with 1,000. And notice that's how the equation is built. Okay, starting with the y-intercept, and in this case we are adding the slope times t. Okay, and that's how linear equations are written.